Assalamu alaikum warahmatullah. Now we move on to vector spaces. So vectors, they belong or they live in a vector space. A vector space is a group with a set, and we have defined two operations on it, the vector addition. So we have two vectors. So the vector additions take two vectors from the same set and give you a vector in the same set. So it is a close operation under the addition, right? And scalar multiplication here. So we take a constant, a scalar that belongs to R, multiply it by V, and you get another vector. So it's scaling of the vector, right? So where we have it's an abelian group, the vector set and addition. Now I think we need to go down a bit, just over the exercises, examples, and back to the text. Here's the text. Okay, so this is the first thing. The second thing that we need to check is the distributivity. So we have scalar and x and y in the candidate subspace or vector space here. So lambda can be distributed over the addition, right? The second thing is that here we have associativity with respect to the scalar multiplication. So if we have two scalars and one vector, so we can change the order of scalar multiplication, right? Finally, we have the neutral element with respect to multiplication, scalar multiplication, of course. And this is only 1. If we have 1 times x, it equals x for all x's. Okay. A few examples that we have of vector spaces. Fortunately, we have the Rn, meaning the vectors, and here we have the matrices, and here we have the complex numbers. Okay, so let's explain them. Okay, right. Okay, we said first one is the vector. Vectors are a vector space. So let's check the first thing. So we have this, the vectors, and we have addition and multiplication, scalar multiplication. Of course, they must be closed, right? So meaning that if we have for all x and y that belong to Rn, let's say, the addition should be associative as well, give you another vector, say z, and this intuitively belongs to Rn, right? You cannot find any z vector that does not belong to Rn. Okay. Similarly, for all, so now we need to check the closure under the, let's say, the, what do they call it? So, okay, so it's okay. The multiplication, scalar multiplication. So for all lambda in R and x and Rn, lambda times x belongs to Rn, right? So you just scaled the vector and still in the Rn. So this means that we have closure, which is good. Second thing, distributivity over addition. say lambda times x plus y, where x and y of course belong to Rn. So let's state that. Okay. Okay, so here x and y belong to Rn, and lambda belongs to R, of course. We have lambda times x plus y equals lambda x plus lambda y, and we have shown that lambda x belongs to Rn, lambda y belongs to Rn, so this belongs to Rn as well, which is good. Of course, lambda and phi, so let's say phi also belong to Rn or R, sorry. You can change the order easily, right? So this is not a big deal. Okay, so we have shown that what, sorry. Okay, now that's good. Okay, now let's take the other example, which is, of course, I think we have forgot to say that the neutral element, right? So we need to show that the neutral element for the multiplication, scalar multiplication, which is the neutral element is 1. So neutral element here, neutral element is scalar 1, so there's no problem in that, right? Now our next example is the matrices. Same thing, addition and scalar multiplication, so it's very simple, right? So for A and B belonging to R M cross N, of course C A plus B also belongs to that same space, and for lambda in R, can easily show that lambda A also belongs to the same space, so it is closed under addition and multiplication, so it's a simple thing. Of course, distributivity, again, you have lambda times A plus B equals lambda A plus lambda B, and this equals to the same space. No problem in that. And associativity for the multiplication, lambda times phi A equals lambda phi times A, so it's very simple. And the neutral element for the addition, or sorry, for the multiplication, here the neutral element is what? Lambda equals 1, the same thing, so it's a vector space. Let's look at the last case, which is the complex numbers, C. Okay, so the first thing, so let's say we have x that belongs to C, x and y, x and y. So let's say x equals A plus JB and y equals C plus JD. x plus y equals a plus jb plus c's plus jd, which equals a plus b plus c plus j times b plus d, right? So we can call this e plus jf, right? And this belongs to the complex numbers. Very simple. Now say lambda equals, belongs to r, and say lambda x, it's lambda times a plus jb, which is lambda a plus j lambda b, and this again is in the complex set. No problem with that. As for the associativity, so lambda times x plus y, we can easily show that it's lambda x plus lambda y. No problem with that. And the neutral element, I think this would be very simple as well, right? So the neutral element with respect to the multiplication, it is what? Lambda times x equals x, lambda here equals 1. So again, let's write it correctly. So right, lambda. It's very simple. So let's go back. So we have shown that all those three are vector spaces.